Good evening. Hello. Good evening. Varshita, Chaitanya, Manish, and Asta.
Yes,
Let us just wait for another 2-3 minutes since there are only 4 candidates as of now. Okay, let's start then. No improvement in attendance anyway. So, welcoming you to contact session 5. And today's topic contains the contents of finding eigenvalues and eigenvectors of matrices, and also properties of eigenvalues and eigenvectors. Let us first get motivated as to why we find the eigenvalues and eigenvectors. And how do we go about? Let's go in detail. And what will happen if, and what do you mean by eigenvalues, which are the solutions of the characteristic equation of the matrix A? And what is the meaning of characteristic equation of the given matrix A? So all those things we will see in detail. And this is an important topic. And from exam point of view too, you will be able to easily grasp and reproduce, and then you'll be able to do problems on your own. Look at definition and examples of eigenvalues, computation of eigenvalues and eigenvectors, properties of eigenvalues and eigenvectors as I already listed. Look at this. Every matrix multiplication with the vector stretches, means it elongates the length and rotate the given vector. So it has both magnitude and direction as any vector has. But here, when you have the matrix multiplication with a vector, it extends, it stretches, and also goes through a rotation. What do we mean by that? Just look at. Consider a vector x, 1, 3. Of course, here it is given with a bar also. Even if you don't put bar, no matter. That's the reason why we used to the bold face. Okay. So x is the column vector 1, 3. And A is the square matrix 2, 1, minus 1, 1. On multiplying this vector with the matrix A, we get y equal to ax. So we just call this as some y. Isn't it something like a kind of transformation? So x gets mapped into y through the matrix A. So you have y equal to ax, something like your f of x equal to y, isn't it? So vector y is equal to, it's yet another vector, isn't it? When you multiply matrix of order 2 by 2 and with another matrix, in fact, it's a column matrix, but it's a vector here. So which is a 2 by 1. Therefore, matrix multiplication in that order, A into X, 2 by 2 into 2 by 1, isn't it? So you have, the result will be a 2 by 1 matrix. 2 by 2, look at, this is 2 by 2 and this is 2 by 1. So number of row columns of the first matrix is the same as number of rows of the second matrix. Therefore, the product is defined and the resulting matrix will have its order 2 by 1. That is 2 into 1 plus 1 into 3, that is 2 plus 3, 5. 2 plus 3, 5. And minus 1 into 1 plus 1 into 3, 3 minus 1, 2. So you have a column matrix. In other words, it's a vector actually, isn't it? A column vector. So what is happening here? Suppose this you take 1, 3, the vector, as a point. As a point, when you plot on the two-dimensional plane, as 1, comma 3, that is on the x-axis you have 1 and on the y-axis you have 3. So it is the point 1, comma 3 or the vector 1, 3. And next, after getting it multiplied with the matrix given, you have vector y, which is 5, 2. So that is x coordinate is 5 and y coordinate is 2. Something like your point 5, comma 2. It's a vector 5, 2. So just look at here. This is stretched, isn't it? And also it has gone through a rotation. So from this direction, it is rotated through this one. So here you have the stretching, that is the lengthened, it is extended, and then also gone through a rotation. Okay, so this leads to finding eigenvalues of the given matrix. We will see one more example where what's happening, we'll see. From the above figure, it's clear that the matrix multiplication with vector. So we are bringing in the concept here, matrix multiplication with the vector, which stretches and rotates the vector. That is change of direction of the vector, isn't it? Almost all vectors change direction when they are multiplied by a matrix A. But certain exceptional vectors are there in the direction as Ax. So in general, when you multiply a vector with a matrix, definitely it gets stretched and also gets rotated through. That is, the direction gets changed. But there are some exceptional cases where there will only be stretching, but not a rotation. So that also we will just see. For example, let us take a square matrix A equal to minus 6, 3, 4, 5 and a vector x, 1, 4 and find out the product Ax. You have minus 6, 3, 4, 5 into 1 by 1, 4 is, you have that is matrix multiplication minus 6 into 1 plus 3 into 4, that is 12 minus 6, 6. 4 into 1 plus 5 into 4, 20 plus 4, 24. So you have a column vector 6, 24. This can be written as 6 times 1, the column vector 1, 4, because you know very well, it's basically a matrix, isn't it? So any of the or every row and column of the matrix can have a common multiple, isn't it? So you can multiply, so you can take it out. So 6 times it is 1 4, which means that this scalar can be multiplied by every element of the matrix, so that it is 6 into 1, 6 into 4. So that is, it is 6 into 1 4. But this 6 is a scalar, which is denoted by lambda. This lambda is going to be called later on, under certain condition, an eigenvalue of the given matrix. When, we will see. So we are now bringing in, not just by putting any scalar by symbol C or K or whatever it is, we start using the notation lambda, which is which gives rise to the motivation for getting eigenvalues and eigenvectors. And therefore, now, so eigenvalues are nothing but it's going to be the solution or the values of solving a square quadratic equation or a cubic equation or a fourth degree equation and so on, depending upon the nature of the order of the matrix for which you are finding the eigenvalues. Eigenvectors are nothing but the vectors that are corresponding to that which we find corresponding to those eigenvalues we find for the matrix in question. So this 6, any scalar, that we will denote it by lambda. So we started with ax, and then we are having an equation lambda x. Okay, so any vector given multiplied by a square matrix, and then it gives rise to a constant multiplied by the same vector is also possible. So ax equal to lambda x is possible, isn't it? So in this case, what is happening? What is the original point here? Your vector is 1, 4. So if you take it as a x coordinate 1 and y coordinate 4, you have the point 1, 4, or the vector 1, 4, you take it as it is. Now, what is the vector y now? It is, that is your ax 624, isn't it? 6 times 1, 4. 624 is actually the vector that is against 6 on the x-axis and 24 against the y-axis. So it is your ax vector or y vector, but that is written as 6, 1, 4. So what's happening here? The direction is not changed. So original vector is the column vector 1, 4, and after multiplication with the given square matrix, it gets stretched to, it gets elongated, it gets lengthened to a vector 6 for 624, which is nothing but 6 times the given vector x. Is it right? So therefore here there is no changing of direction, but there is only a stretching. So here A only stretches the vector x by magnitude 6 times according to this problem, but not changing the direction of vector. So there are instances where this kind of equality, that ax equal to lambda x, is possible. So this is the motivation behind getting into the concept of finding the values of lambda, which are going to be called eigenvalues. What is that? So we can hereafter start with the equation ax equal to lambda x. Call it as equation 1. So that kind of equation is justified, we have seen. Okay. So where A is a given square matrix. Lambda an unknown scalar, real or complex. Okay, it can be real or complex. And x an unknown vector. So what we have come to know about? The task is to determine lambdas and x's that satisfy equation 1. So finding the value, determining the values of lambdas will give you the meaning that we have found out the eigenvalues. Finding the vectors x depending on the values of lambda correspondingly will give rise to the vectors being called as, therefore, eigenvectors. Okay. Since x equal to 0 is always a solution for any lambda, we only admit solutions with x not equal to 0. We know very well x equal to 0 is a trivial solution, isn't it? So when you have x0 vector, left hand side is 0, right hand side is also 0. Therefore, that is trivial, that is obvious. And therefore, we are interested only in non-trivial solutions. That is, x is not equal to 0. So the solution vector or the eigenvector should be a non-zero vector. In the sense, when you have, suppose you have the vector 3 components, x1, x2, x3. it should not all components should be zero. There can be zeros. Some of the components can be zero, but not all of them. If all of them are zeros, then it becomes a zero vector, which should not be the case. So even if there is one non-zero component, it is a non-zero vector. So that is what we are interested in. So the solutions to equation 1 ax equal lambda x are given the following names. The lambdas here, the lambdas means the values of lambda that satisfy equation 1 are called the eigenvalues of the matrix A. And the corresponding non-zero underline non-zero x's means non-zero values of the vectors x that also satisfy equation 1 are called eigenvectors of. So this is where we start our definition of eigenvalues and eigenvectors of given matrix. Now, so where do you get this equation and how do you form your characteristic equation of the matrix? Let us see all those things. And we are already familiar with some n by n linear equation, a system of linear equations in n unknowns. Okay, so let us now write. This example illustrates the general case as follows. So what you have written as ax equal to lambda x can now be elaborated. If a equal to aij, small aij within brackets, I equal to 1 to n, j equal to 1 to n, because it's a square matrix. And left hand side you have lambda x, where x is having components x1, x2, etc., xn, because it's A is a matrix of order n by n. Therefore, if you expand ax equal to lambda x, that will give rise to equation, a system of linear equations, isn't it? N rows and n columns on the left hand side. That is a11 x1 plus etc. plus a1n xn equal to lambda times x1. a21 x1 plus etc. plus a2n xn equal to lambda times x2, etc. And nth row an1 x1 plus etc. plus ann xn equal to lambda xn. So this is what exactly the expansion of your equation 1. Now transferring the terms on the right hand side to the left hand side. What do you have? What do you want to have? Transferring the terms on the right hand side. That is, we are bringing in the terms x1, x2, etc. to the left hand side. So that what's happening? a11 minus lambda times x1 plus a12 x2 plus etc. plus a1 n xn equal to 0. Isn't it? 0 is now the integer 0. Each equation is having integer 0. Then second, a21 x1 will be as it is, plus what is the second term in the a22 minus lambda now? Isn't that a22 minus lambda? In the second equation, you will have the second term a22 x2. Look at the right hand side, you have lambda x2. Only that term you will have a22 minus lambda into x2 plus etc. plus a2n xn equal to 0, etc. etc. Finally, what will you have? an1 x1 plus etc. plus ann minus lambda into xn equal to 0. So what do you understand? The principal diagonal elements a11, a22, a33, etc. ann become a11 minus lambda, a22 minus lambda, etc. ann minus lambda. Is it right? So into, of course, x1, x2, etc. xn. Okay. Now, what do we do out of this? Call this set as equation 2, just for reference sake. In matrix notation. So how can this set of equations can be written as capital A minus lambda I into capital X equal to cap O. Why it is lambda I? Because you have in the principal diagonal a11 minus lambda, a22 minus lambda, etc. ann minus lambda. Is it not? So you cannot see when you have subtraction of a scalar from a matrix cannot be done. You can multiply, you can do a scalar multiplication. You can multiply lambda with every component of a vector, but you cannot subtract from each of the, you cannot add or subtract to each of the components of a vector, isn't it? For that, if at all you want to have a subtraction or addition, you must have matrices of same order. So this A1 minus lambda, etc., will therefore become capital A minus lambda I, because if you have A11, A12, etc., A1n, A21, A22, etc., A2n, AN1, AN2, etc., ANN is your capital A minus what is lambda I? That is the lambda times the unit matrix. Lambda times 100, 010, of course, see 10, etc., 0, 01, etc., 0, etc., etc., 000, etc., 1. Is it right? So what will happen? The principal diagonal elements now. Lambda, lambda, lambda. So you are having A11 minus lambda, A22 minus lambda, etc., ANN minus lambda. Is it right? So what is the meaning then? A minus lambda I. Since A is a matrix, since there is a subtraction, so it cannot just be lambda, but it is the matrix. The division or addition will be only between matrices of same order. Is it right? So when A is here of order n by n, I is also of order n by n. If you are practical problems, when you have A is of order 2 by 2, then your I will be 1001. If A is of order 3 by 3, your I is actually 100, 010, 001. Anyway, it's going to be your lambda is being subtracted, so it is going to be I. So set of equations 2 can simply be written in matrix notation as A minus lambda I. I here capital I. That is unit matrix multiplied by vector x equal to vector cap O, that is vector 0 vector. So what's happening? This is a homogeneous linear system of equations, isn't it? Ax equal to 0. We have seen enough solving system of homogeneous linear equations, isn't it? So has a non-trivial solution. This has a solution, that to non-trivial solution, if and only if the corresponding determinant of the coefficients is 0. So we know very well when there is an equation, matrix equation of the form Ax equal to 0, we have solved, and that this system of equations, homogeneous since on the right hand side you have 0, has a non-trivial solution. That is, you have x not equal to 0 when you are going to solve for x, only when the corresponding determinant of the coefficients. So what are the coefficients here? These are the coefficients. Isn't it? A11 minus lambda, A21, etc., AN1 are coefficients of x1. A12, A22 minus lambda, etc., AN2 are coefficients of x2. A1n, A2n, etc., ANN minus lambda are coefficients of xn. Therefore, you have the result that determinant of the coefficients of the components of the vector x. Is it right? So they are the columns of the determinant. First column, second column, etc., nth column respectively, and is equal to 0 is the condition. Okay. So this, of course, we are just denoting by various symbols. Capital D of lambda, that is determinant involving lambda. Okay. And more so, I would suggest that you can simply write this one. Det means determinant of A minus lambda I equal to, when you are writing det determinant, be careful about using the appropriate notation. For matrix, it is ordinary brackets or square brackets. But for the determinant, it is only vertical lines. It's you have only modulus symbol, like something like that, isn't it? So equal to 0 here. Here, this 0 is actually integer 0 because this is going to be determined. So this is going to be a polynomial in lambda, maybe of degree 2 or degree 3. Here it is of degree n. So this is being equated to 0 will definitely give you values of lambda. Two values of lambda if it is a quadratic equation in lambda, three values of lambda if it is a cubic equation in lambda. That is the maximum scope according to our syllabus. So anyway, but here it is, of course, it will be the left-hand side. If you expand, will be a nth degree polynomial in lambda being equated to 0. It will become therefore an nth degree equation in lambda, which upon solving will give you n values of lambda. Therefore, so you know that now to get, so what we are trying to understand now, to get the values of lambda, namely the eigenvalues of the given matrix A, square matrix, of course, you need to find determinant A minus lambda equated to 0. You have to equate it, you have to solve it. And what is this equation? Determinant of A minus lambda equal to 0 is called, it's called characteristic equation of A. Characteristic equation of A. Okay, some authors, they of course they may also be referred to. Because of this characteristic equation, we also say the values of lambda as characteristic values, latent values, eigenvalues. But most widely used, most popularly used, and according to the terms that are being used in your syllabus context, better you be familiar with that they are eigenvalues. But remember that they are also called characteristic values and latent values. But anyway, they are popularly known as eigenvalues. Okay. So we will just now describe what is what. A minus lambda I is called a characteristic matrix because we have written there matrix A minus lambda I into vector x equal to 0 vector. So that A minus lambda I matrix is called a characteristic matrix. And determinant, if you put this symbol, modular symbol, then of course that is also denoted by this author d of lambda. That is determinant A minus lambda I is called a characteristic determinant of A. Equation 4 is called the characteristic equation of A. What is equation 4? As I just now have mentioned, det of A minus lambda I, that is determinant A11 minus lambda, etc. equal to 0 is called a characteristic equation of A. So in short, characteristic equation of A is determinant A minus lambda equal to 0. By developing D of lambda, by developing means by expanding, we obtain a polynomial of nth degree in lambda as far as this question, this description is concerned, because we have taken A as a matrix of order n by n. So we get a polynomial of nth degree. So if you're having A is of order 2 by 2, we get second degree polynomial in lambda. Is it right? So this is called the characteristic polynomial of A. But anyway, we are having the equation to solve for lambda so that it becomes characteristic equation of A. See, the eigenvalues of a square matrix A are the roots of the characteristic equation 4, which we have referred to of A. So what is important now? Practically speaking, given A, find out straight away determinant A minus lambda equal to 0. You take it straight away. So determinant, what do you mean by A minus lambda I? The principal diagonal elements will have minus followed by lambda, unknown as of now. And A11, A22, A33, etc. will be available in your question, isn't it? And other elements will be as they are. Equal to 0, expand that characteristic polynomial in lambda so that it becomes a characteristic equation in the characteristic equation of A, that is a second degree or third degree or fourth degree equation in lambda, and equated to 0. So you can solve for lambda. Such of those values of lambda are also called roots. You know very well, when you solve a quadratic equation in a variable x of the form ax square plus bx plus c equal to 0, are given by x equal to minus b plus or minus square root of b square minus 4ac whole divided by 2a. Is it right? Where a and b are known as coefficients of x square and x, c is the constant. Is it right? You have plus or minus. So you have two values of x. So they can be simply said two values of x are solutions, or we can also say roots. So we use the word roots. Okay. So the roots of the characteristic equation are the eigenvalues. Hence, an n by n matrix has at least one eigenvalue and at most n numerically different eigenvalues. Okay, right. The eigenvalues must be determined first. So that's what we have understood from the deliberation so far. Once these are known, corresponding eigenvectors are obtained from the system of equations that we have. For instance, by the Gauss elimination, where lambda is the eigenvalue for which an eigenvector is wanted. Anyway, so this is just description. When you are going to do actual problems, you will come to know what exactly you mean by using lambda and finding the corresponding eigenvector. Okay, by Gauss elimination method or some other method that can be put into practice. Let's see. Now, before we go deep into the practical problems, we'll just share some more results. Eigenvectors, eigenspace. If W and X are eigenvectors of a matrix A corresponding to the same eigenvalue lambda, so are W plus X provided X not equal to minus W. Because if X equal to minus W, we get 0, isn't it? So we should get only non-zero vector. And Kx for any K, any scalar not equal to 0. Okay. So this is one thing you are looking at here. We just look at corresponding to the same eigenvalue lambda. So supposing you are going to see all those things in practice and you are going to have exercises and before that illustrations. Suppose you have a matrix of order 3 by 3. Then you have a cubic equation in lambda, which is the characteristic equation of your A. And when you solve, you get 3 values of lambda. All the 3 may be equal and 2 of them may be equal. So when you have 2 eigenvectors corresponding to the same, 2 different eigenvectors corresponding to the same eigenvalue, that is possible. We are going to see. Then their addition and the scalar multiplication are also eigenvectors. Okay. Then hence the eigenvectors corresponding to one and the same eigenvalue lambda of A, such of those eigenvectors together with the zero vector form a vector space. So corresponding to one and the same eigenvalue, but 2 different eigenvectors, if you are able to follow, if you are able to get, then they will form a vector space called a eigenspace of A, corresponding to that particular lambda. Now, some more definitions. So these are all will be highly useful in answering MCQs. The set of all the eigenvalues of A is called the spectrum of A. So you have, again, lambda equal to 3 eigenvalues or lambda equal to 2 eigenvalues depending upon the nature of, order of A. So the set of such eigenvalues will be called a spectrum of A. Everything is for A, for the given matrix A. We shall see that the spectrum consists of at least one eigenvalue and at most n numerically different eigenvalues. Okay. The largest of the absolute values of the eigenvalues of A is called the spectral radius of A. So what do you mean by absolute value? Suppose you have minus 4, 1, 2, 3 eigenvalues, suppose. And which is actually greater? 2. 2 is the largest. Isn't it? 2 is greater than 1. 1 is greater than minus 4. But here, what is given here? Absolute values of the eigenvalues you need to find. Modulus of minus 2, minus 4 is 4. Modulus of 1, 1. Modulus of 2, 2. So even though minus 4 is the least when it is an eigenvalue, but when you take an absolute value of it, it becomes the largest of the given eigenvalues that you are having. So that, and that is called the spectral radius of A. So when you have minus 4, 1, 2, you can't say 2 is the spectral radius, but when you take absolute values, modulus of minus 4 becoming 4, which is the largest of 1 and greater than 1 and 2, becomes the spectral radius of A. That's why it is given that the largest of the absolute values of the eigenvalues is the spectral radius of A. Now, let's start with finding simple matrix A in the sense of order 2 by 2, the eigenvalues and the corresponding eigenvectors. Of course, in this problem, it's also given to find the eigenspace, but more in general, mostly will be only asked to find eigenvalues and eigenvectors. Of course, when you have the eigenvectors, you can have its span to be the eigenspace. Okay, so how to get eigenvalues? So first, here of course it is given. Here first it is given the uh, matrix equation A minus lambda x equal to 0 to be solved for the vector x, namely the eigenvectors corresponding to eigenvalues. So in my opinion, I would suggest that better you first go for finding eigenvalues first. Okay, so write first the characteristic equation of A is determinant A minus lambda equal to 0. Instead of even writing det, you can straight away put the determinant symbol. So here better you can write here. I would suggest you can start first finding the eigenvalues. Okay, right? The characteristic equation of A means of the matrix A. Yes, you can straight away put the symbol instead of writing det, determinant symbol. A minus lambda I equal to integer 0. Is it right? Right? Right. So what is the meaning? What is this actually? This is here. This is here. So this is how you just start first. So determinant, you just look at what do you mean by determinant A minus lambda I? You just go for your matrix A. In the principal diagonal elements, from the principal diagonal elements, you subtract lambda. Only from A11 minus lambda, A22 minus lambda. That is what we mean by A minus lambda I matrix, isn't it? So when it becomes determinant, the same. You have minus 5 minus lambda, 2 as it is,
Excuse
2
me, sir.
as it is. Yes, yes, yes. Any doubt?
Sir, what are you writing on the PPT is not recording, sir. Actually, when we are going through it again, we are unable to see that what you are writing on the PPT. It is not recording.
Oh, it's not remaining there, huh? Okay.
Ah,
Anyway,
yes,
but
sir.
okay, okay. But anyway, nothing new is written here. I just only written the term, the characteristic equation of A. That's all. So you can just write first the characteristic equation of A is determinant A minus lambda equals 0. See, that is what here it is written. I just put at the term the characteristic equation of A is. So that will give you an idea that you are starting with the characteristic equation of A, which you won't forget to write. Okay. That's all. Right? Is it clear now? Is it okay?
Yes, sir. But in previous PPTs, you have done some problems also that step by step, and that is not recorded. We are unable to understand.
Normally it will be there, when it is annotated, it should remain. That's
No,
what
it
I
is
have.
not there in the recording, sir. We have checked.
Oh, is
The
it?
red one which you are writing, it is not recording only.
Oh, no, but everything gets recorded, because when it is annotated, um, there's the first time that I'm hearing from you that it is not there. It gets
Yes, sir.
erased. I don't know. I haven't been given that kind of feedback at all. It's the first time I'm hearing. Anyway, I will check, I will see how I can retain. See. So you just follow now. Okay. Right. Otherwise, I have to go to whiteboard and then start writing. I think it will be there. I will try. Okay. Okay. If need be, wherever there is any
Excuse me,
escalation.
sir.
Yes. Yes.
For me also, it's not visible, sir.
Where?
On the recordings.
Yeah. That's what one student has shared now. Given the
Yes, sir.
feedback, I will check. Okay. I will check.
Okay, okay, sir.
Okay. Right. Right. I will check. Okay, you just follow now. Everything is written here. I just have given more information. That's all. You can write the characteristic equation of A. Okay, right. So you just see here. So this one. Now you know how to expand a determinant. This is very simple. 2 by 2. So you will first multiply these principal diagonal elements, isn't it? Minus 5 minus lambda into minus 5 here, minus 5 minus lambda into minus 2 minus lambda minus then product of the other two secondary diagonal elements minus 4 minus 2 into 2, 4. So this is how you expanded 2 by 2 determinant equal to, you simplify, now you have to simplify this. Minus lambda into minus lambda plus lambda square. You have minus 5 plus 5 lambda plus 2 lambda. So you have plus 7 lambda. Then here minus 5 minus 2 becomes 10, minus 4 equal to plus 6. So it's very simple that upon expanding the 2 by 2 determinant on the left hand side, you have a polynomial, or in short, a second degree expression in lambda, which is lambda square plus 7 lambda plus 6 equal to 0. Now, can you give me immediately the values of lambda without taking recourse to taking the formula being a quadratic equation in lambda where a equal to 1, b equal to 7, c equal to 6? You know how to solve by formula, or you can go for factorization, whatever it is. Now you must be in a position that you might have studied well in your school days itself, that what are the values of lambda when you solve this quadratic equation? Can anyone say immediately what are the values of lambda? You can say immediately. The two values of lambda will be minus 1, minus 6. Isn't that? Because if you take the middle term, if you take the middle term, it is 1 plus 6 and 1 into 6. But you have to check the coefficient of lambda square, which is 1. Therefore, middle term, if you split, it is factorization anyway. 1 plus 6, this is 1 into 6. So many of you are in the habit of writing, therefore, when you do by factorization, you will simply write lambda equal to 1, lambda equal to 6. This is a very commonly occurring mistake that we have been finding quite often in the solutions, in the examinations. So when you do by factorization, care must be taken that it is actually lambda plus 1 into lambda plus 6 equal to 0, so that lambda will be, many of you will not be writing it lambda plus 1 equal to 0 or lambda plus 6 equal to 0, so that lambda equal to minus 1 and lambda equal to minus 6. They will immediately jump to the conclusion that lambda equal to 1, lambda equal to 6, which are wrong. So that everything will go wrong. So therefore, in this context, I would suggest to you better you solve by formula. Lambda equal to minus b minus 7 plus or minus root of b square 49 minus 4 into a 1 into 6 4ac whole divided by 2 into 1. You will get two values of lambda to be clearly minus 1 minus 6. If you do by factorization or even just by looking at, you will be able to solve 1 plus 6 7 and 1 into 6 6. Therefore, the two values of lambda are not 1 and 6, minus 1 minus 6. Is it clear? Is it true or not? Hello?
Yes, sir. Yes, sir.
Okay, right. So look at, so let us not go deep into all these statements written here. So you just look at lambda 1 equal to minus 1, lambda 2 equal to, so we can just describe them as, since there are two distinct eigenvalues, we can write them as lambda 1, lambda 2, minus 1, minus 6. Okay, but these are the eigenvalues of A. Right. Now, corresponding to each of these eigenvalues, we need to find eigenvector. So let us take eigenvector of A corresponding to lambda 1. That is lambda 1 equal to minus 1 in equation 1. Well, we will be preparing this set of equations by putting lambda 1 equal to minus 1, etc. hereafter. But anyway, nothing wrong. The author has used, already he has taken this characteristic. He has taken the equation a minus lambda into x equal to 0, because we are going to solve for x. So you must take the equation a minus lambda into x equal to 0, 0. That is vector 0, or you can put it as the components. Okay. So a minus, better you can write, this is where you have to start in the second portion. Now we need to get values of x. That is vector x1, vector x2. There are two vectors will be there because corresponding to lambda 1 and lambda 2. Okay. So what is the general equation? Ax equal to a minus lambda into x equal to 0 is going to give you the vectors x, which are going to be called eigenvectors corresponding to lambda 1 and lambda 2 in this case. So that is already taken care of here, which of course you can do after finding the eigenvalues. That would be nice. Okay. So let us expand -5 minus lambda into x1 plus 2x. It's matrix multiplication equal to 0. When two matrices are equal, corresponding entries are equal. So when this 2 by 2 and this 2 by 1 are multiplied, you get it 2 by 1. That is, you get only one element on the one element, then another element. That is, you get a 2 by 1 matrix on the left hand side and 2 by 1 matrix on the right hand side is 0, 0. In other words, the first simplification is equal to 0 and second simplification equal to 0, so that they become a system of two linear equations in two unknowns, x1 and x2. Just look at -5 minus lambda into x1 plus 2 times x2 equal to 0. Then 2 into x1 plus -2 minus lambda into x2 equal to 0. This is the system of linear equations in two unknowns x1 and x2. So x1 and x2 will be the components of your vector x, which of course we can call it as x1. For lambda equal to lambda, for lambda equal to -1, that is lambda 1 value. Then for lambda 1 value, another lambda 2, for lambda 2, we will get x2, we can say. But each of the vectors will have two components because you have the unknowns are two in number here. Okay. So when you, this is the system of equations. Now put lambda equal to -1. Now come back here. Put lambda equal to -1 in that equation, which of course we are preparing now, or you can do it earlier, nothing wrong in it, but I would suggest that you can start now. So you get now, just see, -5 minus lambda, is it not? So -5 minus lambda becomes -5 plus 1. So you get -4x1 plus, just go there, plus -4 plus 1, that is -4x1 plus 2x2 equal to 0. Then 2x1 plus, this is -2 plus 1, so -x2. 2x1 minus x2 equals 0. So thus, by putting lambda equal to -1, you have these two equations. Now look at how will you solve. You know how to solve ordinarily by elimination method, is it not? Or by reducing into echelon form, then by back substitution method. But here being a simple equation, you can easily see that this equation is nothing but multiple of the second equation. They are in fact one and the same. If you take out -2 outside, this is 2x1 minus x2 equals 0. Isn't it? Which means these two equations are one and the same. Therefore, you cannot solve by finding individual values straight away. So here one variable is depending on the other. So you have to go for assumption. So since these two equations are one and the same, and you can take any one of them and you will see that 2x1 minus x2 equals 0. This is also 2x1 minus x2 equals 0. So take naturally available only one equation and write one in terms of the other. So what you can take either from this or this the same. 2x1 minus x2 equals 0 means you are not able to get independent values x1, x2 straight away, but one is depending on the other. X2 equal to 2x1. So you have to go for assumption. If you give assumption, if you assume value for x1, you will get x2. Or if you get value for x2, you will get x1, isn't it? But it is x2 is 2 times x1. So better you can start the assumption with x1. And remember, in general, there is no hard and fast rule that you should not get components of a vector as decimals. But in general, we take the whole numbers. We don't go for decimals. So vector and and you should only be non-zero vector, and therefore you start with the assumption always to be +1. Okay, so put x1 equal to 1 to be on the safer side. And we obtain the eigenvector, then 1, 2. You may ask one question. Can't we take x1 equal to 0.5 so that x2 equal to 1? Yes, nothing wrong. But in practice, in general, we don't take the decimal values. We don't take fractions. But you may get, you can write, nothing wrong in it. That's the reason why the eigenvectors are not unique. Because, in fact, if you are going to have about, suppose, a system of 3 equations in 3 unknowns, you can either get it reduced to echelon form and then by back substitution you can find the unknowns, or by cross multiplication method, which you might have studied in your school days, which are going to be only proportional values, not exact values. Proportional values. So when you say proportional values, when you say x1, x2, x3 are in the ratio of, say, 1:2:4. So the values themselves can be 1, 2, 4, or 2, 4, 8, or 3, 6, 12. It can be in multiples when they are in the ratio, when they are proportional, isn't it? And therefore, the value, the eigenvectors are not unique. Okay, right. So that is going to be again emboldened, that will be vindicated by some other answers which we are going to see soon. Okay, so your x1 is 1, x2 is 2. So the x1, x2 forms the two components of your vector x for the first eigenvalue lambda1 equal to -1. Therefore, we can write, as I just already mentioned, x, not just x, but x1 corresponding to lambda1 is the vector, column vector 1, 2. Okay, that's all. Let's answer. For your lambda1 equal to -1. Well, there is a checking ax1, you have -1, -2 when you multiply actually, and -1 can be taken out. -1 x1 equal to lambda x1, lambda equal to -1. Well, this checking is not necessary. In practical problems in the examination, this checking is not necessary. Similarly, put lambda equal to -6. So what you will get? -5 plus 6, you get 1x1 plus 2x2 equals 0. And then 2x1, and then you had, what did you have here in the second equation? -2 plus 6 now. Therefore, you get +4. So these are the two equations. Here again, the second equation is nothing but the first equation. They are one and the same. If you take 2 out, it is x1 plus 2 x2 x0. Therefore, what is the meaning? You will not be able to solve uniquely the values of x1 and x2 because there is only one equation but two unknowns, which means what? You will have infinite number of solutions, or in general, you will have many solutions. In other words, one is because that is the reason. The reason is because one is depending on the other. They are not independent. So we can write x2 is equal to, from this, minus 1 by 2 x1. Isn't it? So if you put x, so here again, the same argument can be done. Can't we put x1 equal to 1, as you said, as you just said in the, for the last case? Yes, you can put. Then x2 will become minus 0.5. Nothing wrong. But normally we don't do it. Therefore, in order to make this as a whole number, you take x1 equal to 2. So that x2 equal to -1. You can have negative integer, nothing wrong. Okay, therefore, you have thus the vectors x1 equal to vector 1, 2, column vector, and x2 is equal to, it will only be column. We don't need to every time mention 2 minus 1. Okay. So what is the answer? Eigenvalues are, finally you have better, you sum it up. Therefore, the required eigenvalues are lambda1 equal to -1, lambda2 equal to -6. And corresponding eigenvectors are x1 equal to the vector 1, 2, and x2 equal to vector 2, -1. Okay. So it is here, it is also asked eigenspace. So eigenspace corresponding to lambda1 is lambda1 equal to -1 is span of x1. That is all those vectors that are getting spanned, but is 1, 2 and span 2, -1. In the sense, you can have proportional values of x, as I mentioned, 2, 4, etc. That's the meaning of here span. So you can just write span of span. So you get space of vectors. Okay. Now, we don't need to go deep into this again because determine the eigenvalues and eigenvectors of matrix A having 2 by 2 order. Okay, the same type of problem you can just go through. It's going to be easy. Now, let's go for a 3 by 3 matrix. Find the eigenvalues and eigenvectors of A where you are having matrix of order 3 by 3. Okay, right. So before you consider the equation, you can consider this one, nothing wrong, or you can take it up later. As I mentioned, I would suggest start with a. This is what exactly I have written there. It is written here. So what I want you to do first, write the characteristic equation of A is determinant A minus lambda equal to 0. Here don't bold it. It is only integer 0 because this is going to be a polynomial in lambda, so that this will become an equation, so that this is only integer 0 value. Okay. So now what is your A minus lambda I? Just look at your A, subtract lambda from only the principal diagonal elements so that the other elements will remain the same. So determinant symbol 7 minus lambda minus 2 as it is, minus 14 as it is, 5 as it is, then minus 4 minus lambda minus 7 as it is, 5 third row first column minus 1 as it is, and the third row third column minus 10 minus lambda. In other words, only principal diagonal from principal diagonal elements you will subtract lambda. So that this, of course, I want you to do the expansion. You know very well in the second session itself and third session also, it was reinforced how to expand a 3 by 3 determinant, and that will be the maximum you will be getting in your practical problems. So you will expand through any row. You can expand through any row or column, but uniformly I taught you to have a kind of expansion through, say, first row. Fix it so that when you do the expansion, you will have 7 minus lambda with no preceding sign because it is plus of, multiplied by its minor. So you will have minus 4 minus lambda into minus 10 minus lambda minus plus 7, isn't it? Then positional sign for the second element minus. So it is minus of minus 2 plus 2 into the minor will be 5 into minus 1 minus 10 minus lambda minus this minus 35. So plus 35. And finally, the positional sign for the first row third column is plus. So it is minus 14 into what we have. Its minor will be 2 by 2 determinant upon expansion minus 5 minus 5 into this minus 4 minus lambda. So I just leave it to you. It's going to be simple. You must have already tried your answer. Expansion of 3 by 3 determinant, and we have seen enough. So this gives rise to this cubic equation. So the left-hand side upon expansion is giving you a polynomial in lambda of degree 3. In other words, equated to 0 so that it becomes a cubic equation in lambda. Lambda cube plus 7 lambda square plus 15 lambda plus 9 equal to 0. Now, how to get the three values of lambda? Can anyone say? Do you have any idea? Three values of lambda, how will you get? Hello? Anyone? Any response? No one? Varshita? Nitesh? Or anyone else? No. Okay. So what you do is substitute. This is for one value of lambda is to be found by trial and error method. In other words, you have to substitute a value of lambda and which satisfies this equation. That is, when you put value of lambda equal to 1 or minus 1, something like that, the left hand side should be equal to right hand side. That is the meaning of satisfying the equation, isn't it? So then you may ask, how many times we can try and what are the values that we can try at random? So in general, always you first start with the plus 1. If not, if doesn't satisfy, go for minus 1. If not, you go for plus 2. If not, minus 2. If not, plus 3. If not, minus 3. Maximum, you will not go. Definitely, there will not be any occasion that you will have to go beyond 3 or minus 3. Okay. So mostly you will get between these 6 values, one value of lambda by trial and error method. So let us start with lambda equal to 1. So automatically you will come to understand that when you put lambda equal to plus 1, everything is going to be here 1 plus 7 plus 15 plus 9, which cannot be 0. So that itself shows that lambda value will be minus. So start lambda equal to minus 1. So what we have? Minus 1. Here plus 7 into 1. So minus 1 plus 7, 6. This is minus 15 plus 6. So plus 6 minus 6 equal to 0. Isn't it? So lambda equal to minus 1 satisfies this equation. Clear? Is it clear? Hello? By substitution at random by trial method, you substitute a value for lambda. First you start with plus 1. If not, try with minus 1. If not, with plus 2. Otherwise minus 2. But it will not go indefinitely. So between these 6 values, definitely you will be able to get. So here lambda equal minus 1 is a one solution. So how to get the remaining 2 values of lambda? This is being a cubic expression or cubic polynomial, a polynomial of degree 3 in the left hand side only you have to consider, divided by the linear factor. What is the factor? When lambda equal to minus 1 is a solution, when lambda equal to minus 1 is a solution, lambda plus 1 is a factor, isn't it? You know very well. Lambda plus 1 becomes a factor. So divide this left-hand side expression by lambda plus 1. So that will give you a quadratic expression lambda square plus 6 lambda plus 9. So you get lambda square plus 6 lambda plus 9. Equal to 0. So when you divide this factor, because lambda equal to minus 1 is a solution, you get lambda square plus 6 lambda equal to plus 9 equals 0. What are the two values of lambda therefore? Can anyone say immediately the values of lambda? Lambda equal to minus 3 comma minus 3. Okay. 3 plus 3, 6, 3 into 3, 9. Therefore, the values of lambda are minus 3, minus 3. Just by seeing minus 3, don't just stop writing only with the lambda equal to minus 3. Because there are 3 values of lambda, because it's a cubic equation. One value of lambda is minus 1. Therefore, there are 2 values for lambda by solving the quadratic equation in lambda. Therefore, don't just say lambda equal to minus 3. Don't just stop with that. Minus 3 comma minus 3. Remember, the eigenvalues, that is solution of any quadratic equation, can also be equal. So don't just say the one value only. And this is yet another mistake that many of the students are committing. So you have therefore 3 values of lambda: minus 1, minus 3, minus 3. Okay. Look at, so the eigenvalues are minus 3, minus 3, minus 1. Well, there is no hard and fast rule that you should write it in the order from the negative to positive side, that is the increasing order, minus 3, minus 3, minus 1. You can write any way you like. You know? Okay. So the corresponding eigenvectors are. So how do we get these eigenvectors? I'll just show you because. Well, it's 5:19. Shall we have a break for 5 minutes and then resume the class? Hello? Hello? Can I have a break for 5 minutes and then resume the class? Any response? Hello? Is anyone there? Hello? We'll resume the class after 5 minutes break, okay? Hello. Are you ready? Hello. Hello. Is there anyone to respond? Should I continue? Okay. So, how do you get those eigenvectors? Put lambda equal to -1. First eigenvalue. You will get from your a minus lambda x equal to 0, set of three linear equations, 8x1 minus 2x2 minus 14x3 equal to 0. 5x1 minus 3x2 minus 7x3 equal to 0. 5x1 minus x2 minus 9x3 equal to 0. Okay. So you know how to solve by cross multiplication, where you get only the proportional values of you. You don't need to solve by taking two at a time and then eliminating one of them and then taking a 2 by 2. I mean, two equations in two unknowns, and again go for elimination of one of those two and then go the other one, and by substituting the remaining two, the third one. You don't need to go by that way. You must have studied by, it will take much time to write if I write here. So you get proportional values of the components x1, x2, x3 to be 2, 1. Actually, you are getting like this. Actually, when lambda equal to -1, I just show when lambda equal to -1, when lambda equal to -1, lambda equal to -1, by solving the three linear equations in three unknowns, you get the proportional values of x1 is equal to x2 is equal to x2 by is equal to x3 by actually we are getting -28 -14 -14. So as I mentioned, don't read it as x1 by -28, x2 by -14, x3 by -14. No question of division. They are proportional values. x1 is to x2 is to x3. That means -28, -14, -14, which you can write by completely dividing by -14. You will get x1. This means that is x1 by 2. You divide throughout by -14, or you take out -14, equal to x2 by 1 is equal to x3 by x3 by 1. So this is what exactly your vector. Understood? So when n lambda equal -1 is put, you are having a system of three linear equations by taking two at a time, because you are not solving, you are not finding exact values. So you take three unknowns in two equations, in which case you will only get the proportional values by cross multiplication. You know how to do that. You will get x1 by -28 equal to x2 by -14 equal to x3 by -14. So by dividing throughout by -14, you will get x1 by 2 equal to x2 by 1 equal to x3 by 1. It's not divided by proportional values. So x1 x2, x3 are the components of your vector. Here, of course, they have written the eigenvalues in the order -3, -3, -1. I have taken first lambda equal to -1. Therefore, my vector will be first anyway. So there is no hard and fast rule that which should be first, which should be second. So 2, 1, 1. So your x1, x2, x3 proportional to the values 2, 1, 1 are the values that you have to put for the vector x, x3 or x1, 2, 1, 1. So now next you can take lambda equal to -3. Similarly, you will take two, don't take two identical equations. Okay. Then you will have corresponding, similarly, you can proportional values you can find, and you will get see, when lambda equal to -3, I'm getting only one equation. Other two equations are the same, one and the same. So I'm getting only x1 plus 2, x2 minus 3, x3 equal to 0. There are three unknowns, but there is only one equation. That is the only equation you are having. Other two are the same. So there is a only equation. So in that case, what will happen? You just start lambda equal to -3. You just start then giving some substitution. Okay, you have to because you need to give assumptions for two variables. Only then the third one can be found, isn't it? So when there are three unknowns, but there is only one equation, naturally you need to go for two substitutions, two assumptions. Let x3 equal to 0 and x2 equal to 1. X0 can also be given. Not that every component should be 0, so that it becomes a 0 vector. It should not be. You can give 0 also. Okay, so when there are two or three better when there are three components. So x3 is 0. When x3 is 0 and x2 is 1, you get x3. I put x2 equal to 0. Okay, x3 equal to 0. And I get, where is this? Yeah, I get, of course, by calculation, -4, -20, 0. So that I have, if you divide throughout by -4, I get 1, 5, 0. So in the next assumption, I'm making x2 0. Same equation, I'm making x2 0 so that I will get 7, 5 to be the other elements. That's you are getting corresponding eigenvectors. Well, this diagonalization is not your cup of tea, so that is not necessary now. Otherwise, also I can just get it introduced to you. So if you take these vectors, eigenvectors as a column vectors of your column vectors in your new matrix. I'm forming a new matrix, and that is called the modal matrix. MODAL, not modal matrix. We can denote it by B. Then for this matrix, you know how to find its inverse. By there are two methods, by Gauss-Jordan method, or by 1 by determinant B into adjoint B. It will be inverse. So then the multiplication B inverse A, B will give you the result where you get only the diagonal elements. This is called a diagonalization of the given matrix, where you will get only the diagonal entries. All other elements will be 0. Then it is called a diagonal matrix, isn't it? And that too, you can see that the diagonal elements will be nothing but the eigenvalues. You just see that -3, -3, -1. Anyway. A similar problem you can try. So here is a 3 by 3 matrix, and you have its characteristic equation minus lambda cube plus 6 lambda square minus 3 lambda minus 10 equal to 0. You can factorize, or you can go by substitution for 1, and then you divide by the factor. This is, of course, they have straight away gone for factorization, which you may not be able to do straight away. It is better to go for substitution. Here also you can take lambda equal to -1. This satisfies the equation, so that lambda plus 1 is a factor. So when you divide this cubic expression by lambda plus 1, you will get the quadratic equation, which upon solving, you get lambda equal to 2, lambda equal to 5. So for lambda equal to -1, you get x3 equal to minus 3, 1, 3. Don't take this K3. It is vector X3. Okay. Then lambda 2 equal to 5. You have X2, 3, 1, 3. And this is a mistake actually. Here is a symbol mistake. It should be vector X2. Okay. This should be vector X3. Similarly, this should be vector X1 corresponding to lambda 1 corresponding to lambda 2. This is okay. Then lambda 3, X3. Okay, a similar problem. Then find the eigenvalues and eigenvectors of a similar problem. Then this is algebraic multiplicity and geometric multiplicity. What do you mean by this? Just a minute. The order capital M suffix lambda of an eigenvalue lambda as a root of the characteristic polynomial is called the algebraic multiplicity of lambda. In the sense, when you have repeated value of lambda, for example, in the previous problem, you had lambda equal to minus 3, minus 3. Okay. So here by order, we mean the number of times that the root gets repeated. So repeated roots, only that number is called algebraic multiplicity of lambda. The number of times that the value of lambda gets repeated and is denoted by capital M suffix that lambda. The number small m suffix lambda of linearly independent eigenvectors corresponding to lambda is called the geometric multiplicity of lambda. So the number of linearly independent vectors corresponding to lambda is called a geometric multiplicity. Number of eigenvalues which are getting repeated, only repeated values, gives you the number m lambda, capital M suffix lambda, called algebraic multiplicity of lambda. Because there is a multiplicity means it gets repeated. That's the meaning. Not multiplied by any number. Multiplicity means it is coming more than once. It gets multiplied. It gets repeated. Same way. Here, next one is linearly independent eigenvectors. The number. How many linearly independent vectors are coming corresponding to lambda? Corresponding to same lambda. Is called a geometric multiplicity of lambda. So thus, small m, that is the number of linear vectors is the dimension of the eigenspace corresponding to this lambda. Since the characteristic polynomial has degree n, the sum of all the algebraic multiplicities must equal to n. In the above example, for lambda equal to minus 3, we have m lambda equal to m lambda equal to 2. What is that? What is that m lambda equal to m lambda equal to 2 in the above example? Just look at, we have two eigenvectors minus 2, 1, 0, 3, 0, 1, which are linearly independent. So what is the number of linearly independent vectors? Small m lambda, when lambda equal to minus 3 is 2 for this example. And that is, you are getting two different eigenvectors for the same eigenvalue lambda equal to minus 3 getting repeated. And what is the number of times the eigenvalue lambda equal to minus 3 getting repeated? is 3. So in this problem, actually, look at the eigenvalues are, if you go to this example 2, which is referred to later, 5, -3, -3. So here are the eigenvalues. They get, the eigenvalue gets repeated twice. So -3, -3. So what is the algebraic multiplicity of lambda? 2. 2 times it is repeated, isn't it? Okay. Now, for such a same lambda value -3, you have 2 corresponding eigenvectors. They are linearly independent. Of course, we can check that. We don't need to show. It can be verified. So these are the multiplicity of, these are called geometric multiplicity denoted by small m. So small m lambda is 2. Capital M lambda is also 2. Okay. So in this problem, corresponding to lambda equal to -3, we have small m lambda equal to capital M lambda equal to 2. In general, small m lambda is less than or equal to capital M, which can be shared. So what is the difference? Difference means always denoted by delta. So delta lambda, because everything is for the lambda only. So delta lambda is nothing but capital M minus small m is called the defect of delta. See, delta stands for error. Delta stands for, sometimes, when you take determinant of a matrix in Cramer's rule, delta is also used to represent the determinant, but that is a capital delta. Okay, so otherwise delta normally stands for difference. Okay, so it's called here, we don't use the word delta difference here. Of course, the difference that we are finding is called the defect of lambda. Is an error. Is a error. That's why it's called a defect. We don't use the word defect also. Thus, in this problem, delta -3, that is when lambda equal to -3 is 2 minus 2, 0. But positive defects can also occur. It's not necessary the defect must always be 0. Positive defects can also occur, and there is nothing wrong even if you get defect to be 0. Okay. So here is a problem: algebraic multiplicity, geometric multiplicity, positive defect. So you just go through a simple problem of order 2 by 2, A is of order, and here we find M3 lambda equal to, see, we find it is a matrix of order 2 by 2. So we have algebraic lambda square equal to 0 is your characteristic equation, which means don't immediately say lambda equal to 0. Eigenvalue can also be 0. So lambda square equal to 0 means lambda equal to 0, 0. So 0 gets multiplied. Multiplied in the sense the multiplicity is 2 here, means it gets repeated. So here multiplicity means how many times it gets repeated. So lambda, the eigenvalue, multiplicity, that is its algebraic multiplicity, capital M suffix lambda, that is M suffix naught, because lambda equal to 0 here. Isn't it? Is capital M suffix 0 equal to 2, because lambda equal to 0 gets repeated twice. And you can check your corresponding eigenvector, and that it is 1, small m not equal to 1. There is only one vector. So the defect will be delta not equal to 2 minus 1, 1. So similarly, you can check for the other one also. Now, real matrices with complex eigenvalues and eigenvectors. See, matrices might be real, but you can end up with complex eigenvalues also, and hence naturally complex eigenvectors. Is it right? So how do you get this? You just look at. Since real polynomials may have, remember, real polynomials can have complex roots also. The simplest example, you take any equation, a real equation, a second degree equation in x, for example, x squared plus 1 equal to 0. What is x squared equal to? -1. What is x equal to? Anyone? When x squared plus 1 equal to 0, you must get two values of x. What are they? Can anyone say immediately? Hello? Is there anyone to respond? Hello? Hello? Chaitanya? Varshita? Anyone else? No one is there. Okay. So x square plus 1 equal to 0 means x square equal to minus 1. Therefore, x equal to plus or minus root of minus 1. What is root of minus 1? I, small I, called imaginary number. So plus or minus I. Actually, when you put it in the complex form, it will be plus or minus. See, when lambda square plus 1 equal to 0 is the equation, characteristic equation, this means lambda is equal to plus or minus root of minus 1. Isn't that? That is equal to plus or minus small I. Small I is your imaginary number, root of minus 1. Therefore, you started with a real matrix, that is matrix of real numbers. For example, here it is given A equal to 0, 1, minus 1, 0. The entries are real numbers. And you are finding its characteristic equation determinant of minus lambda 1 minus 1 minus lambda equated to 0. Lambda square minus plus 1 equal to 0, which is lambda equal to lambda square is minus 1 or lambda equal to plus or minus root of minus 1. What is root of minus 1? I, imaginary number. Actually, when you want to put it in the complex number form, x plus iy, it is plus 0 plus 1 into I. Isn't it? Minus 0 plus 1 into I. In other words, you have it is minus I, plus or minus I. Isn't it? That is the complex number. The moment you have the imaginary number, it becomes a complex number of the form x plus iy, x minus iy. Anyway, so it is simply speaking plus or minus I. So there are two values of lambda as usual for a quadratic equation, but are complex roots. And you know very well, when there are two values of lambda and which are complex, they will be complex conjugate. That is, if one is x plus iy, the other one will be x minus iy. Okay. So correspondingly, you can substitute, find out the eigenvector to be, in this case, 1 I and 1 minus I. Now, let's see some more special cases. Eigenvalues of the transpose. So you can easily understand when transpose is nothing but interchanging rows or columns. So transpose, which you write A superfix T of a square matrix A, has the same eigenvalues as A because you are just interchanging the rows and columns. Therefore, naturally, the eigenvalues of A transpose will be the same as eigenvalues of A itself. Basis of eigenvectors. If an n by n matrix A has n distinct eigenvalues, look at the word distinct. So in previous two problems we have come across a matrix of order 3 by 3 having three eigenvalues, of which two are repeated. So there are many occasions where you will get all the three are distinct, different. So if a matrix is of order n by n has n distinct eigenvalues naturally, then A has a basis of eigenvectors which are n in number, x1, x2, etc., etc. for n-dimensional space. So exercises, find the eigenvalues and the corresponding eigenvectors of the following easy 2 by 2 matrices. We finally go to the last topic of the day, namely properties of eigenvalues and eigenvectors. There is going to be a good number of properties which you can visualize by putting your hands at practice of verifying those properties. One or two may be available here, but you can check other properties whether they are true or not. They are true. That you can check. You have to verify. What are they? Sum of the eigenvalues of a matrix is equal to sum of the elements of the principal diagonal. That also you might have studied. If your square matrix is given, then what is it's a trace. Suppose A is the given square matrix. Trace of A is nothing but sum of principal diagonal elements. And that is same as sum of the eigenvalues. See, you can only find the sum of the eigenvalues. You can't here exactly find what are the eigenvalues. Sum of the, of course, when there are some problems where you can find if two eigenvalues are known, the third can be found using these properties. Okay, right. Next, the product of the eigenvalues of a matrix is equal to determinant of the matrix. So the previous one, lambda 1 plus lambda 2 plus lambda 3, suppose it is the matrix is matrix given is of order 3, 3 by 3. Then there are three eigenvalues whose sum is the trace of A, that is principal diagonal element sum, A11 plus A22 plus A33. Product of eigenvalues, lambda 1 into lambda 2 into lambda 3 equal to determinant A. Then a square matrix A and its transpose have the same eigenvalues. The eigenvalues of a triangular matrix are just the diagonal elements of the matrix. Okay. So whether it is an upper triangular matrix or lower triangular matrix or diagonal matrix. Okay, diagonal matrix, you just have only diagonal elements and they are the eigenvalues. And for lower triangular, upper triangular, you have other elements also. It's in. If it is upper triangular, you have elements above principal diagonal. For lower triangular, you have below. But anyway, the eigenvalues are nothing but only those diagonal elements. Okay. Okay. If lambda is an eigenvalue of a matrix A, then 1 by lambda is eigenvalue of A inverse. So these are all most prospective questions for MCQ, multiple choice questions. If suppose you are given 2, 3, 6 are eigenvalues of A, then what are the eigenvalues of A in A inverse? 1 by 2, 1 by 3, 1 by 6, something like that. If lambda is an eigenvalue of an orthogonal matrix A, then 1 by lambda, naturally lambda should not be 0, is also its a eigenvalue. If lambda is an eigenvalue of an orthogonal matrix, when will you call a matrix to be orthogonal? Already you have studied. If A transpose equal to A inverse. If transpose of a matrix is inverse itself, then such a matrix is said to be an orthogonal matrix. Then if lambda is an eigenvalue of such an orthogonal matrix, then 1 by lambda is also its eigenvalue. Okay. If lambda 1, lambda 2, extra lambda n are eigenvalues of matrix A of order n, understood, then lambda 1 power m, lambda 2 power m, etc., lambda n power m are the eigenvalues of what will happen? A power n. Similarly, if lambda 1, lambda 2, extra lambda n are eigenvalues of matrix A, then k times lambda 1, k times lambda 2, etc., k times lambda n are eigenvalues of the matrix k times A. If lambda 1, lambda 2, extra lambda n are eigenvalues of matrix A, then lambda 1 minus k, lambda 2 minus k, etc., lambda n minus k. That means we are subtracting k from each of the eigenvalues will be eigenvalues of A minus, you just can't put k because it is the subtraction of matrices. They should be of same order. So A minus ki, as you got A minus lambda I, isn't it? The k is a scalar. The eigenvalues of a real symmetric matrix are real numbers. See, we have seen just now the eigenvalues of a real matrix can also be complex. But here what we are trying to say, the eigenvalues are real numbers. Remember, for a real symmetric matrix. So if the matrix is symmetric, real, then the eigenvalues must necessarily be real numbers only. Just a minute, I will plug in. Eigenvectors of a symmetric matrix corresponding to distinct eigenvalues are orthogonal. This is a very important property for eigenvectors. So you have come across a matrix having distinct eigenvalues, or two of them are repeated, something like that. But you are having a symmetric matrix and its eigenvalues are all different. Then for such a case, the eigenvectors, if you find, they will be orthogonal. Orthogonal matrix is different from orthogonal vectors. When will you say a matrix to be an orthogonal matrix? Suppose A is the matrix. When will you call it as an orthogonal matrix? If A transpose equal to A inverse. When will you call two vectors to be here actually pairwise orthogonal? Distinct eigenvalues are pairwise orthogonal. Pairwise orthogonal. That means are pairwise orthogonal. That is, supposing there are three eigenvalues which are distinct, then the corresponding eigenvectors, if they are x1, x2, x3, they will be pairwise orthogonal. Orthogonal means it's for a pair. x1 is orthogonal to x2, x2 is orthogonal to x3, and x3 is orthogonal to x1. So pairwise. When will you say a pair of vectors to be orthogonal? Two vectors x1 and x2 are said to be orthogonal if x1 transpose into x2 equal to 0. Okay, so that definition is coming here in 14. That is, so here you have a connection. Just look at two eigenvectors. X1, x2 are called orthogonal vectors if x1 transpose x2 equal to 0. So here you have, they are pairwise orthogonal. So you should know orthogonal. So orthogonality, isn't it? So this orthogonal, here you go, are called orthogonal vectors. Therefore, two vectors x1 and x2 are said to be orthogonal when x1 transpose into x2 equal to 0. So pairwise means x1 transpose into x3 equal to 0, x2 transpose into x3 equal to 0. Therefore, x1, x2, a pair, x2, x3, a pair, and x1, x3 are orthogonal. That's why we say pairwise orthogonal. Okay, right. Okay, right. Next, if lambda 1, lambda 2, extra lambda n are distinct eigenvalues, then the corresponding eigenvectors are linearly independent. Okay. Now, with this background, we just go for now a simple problem. Find the eigenvalue using properties. Okay. Find the eigenvalues and eigenvectors of a square, a power minus 1, and a plus 4i, given a equal to. Find the trace and determinant of A. So we are going to use properties, appropriate properties. So let us first find eigenvalues of A. Okay. Determinant characteristic equation is determinant lambda a minus lambda equals 0 is obtained from the characteristic equation of A is determinant a minus lambda equals 0. That is here determinant 2 minus lambda determinant 2 minus lambda minus 1, 2 minus lambda equal to 0. That is, if you expand this, you get lambda square minus 4 lambda plus 3 equals 0. So minus 3 minus 1 minus 4 minus 3 into minus 1 plus 3. So lambda 1 equal to 1, lambda 2 equal to 3. So the two values of lambda are 1 and 3. Let them be lambda 1 and lambda 2. Let's say 1 and 3. So let us first find, immediately after finding the eigenvalues of A, let us find the trace and determinant of A. What's the property for trace of A? Sum of the eigenvalues of A. Thus, the trace of matrix A of A is 1 plus 3 equal to 4. Okay. So we don't know the principal diagonal elements of the matrix. See, you just, of course, we have here, you cannot say 2 do not mean they are the eigenvalues. Okay. So if you sum them up, that is the trace. We can verify now. So by you are verifying, already you can find trace of A here 2 plus 2, 4. But now we have found eigenvalues to be 1 and 3. So we know that some of the trace of A is sum of the eigenvalues 1 plus 3 equal 4, which is verified. And also determinant of A is product of the eigenvalues 1 into 3 equal to 3, which you can verify here. Even you do the determinant of A, it is 4 minus 1 into minus 1, that is 4 minus 1, 3. So that we have verified. So here, of course, you are given matrix A, so you have found it. Without finding the values, eigenvalues, you will be asked to find a trace and determinant actually, isn't it? So whenever you are given the trace, you can find the sum, but not exactly the eigenvalues, but the product also. Okay. But once the eigenvalues are given, you can find the trace and determinant like that. But here we have found eigenvalues and we have checked, we have verified that the trace of A is already 4, which is here 1 plus 3, correct. And the determinant is by property 1 into 3, 3. So see, you are supposed to use the property and you are verified here. Well, now we will find corresponding eigenvectors for lambda equal to 1 and lambda equal to 3. So when lambda equal to 1, it is 2 minus 1, 1, minus 1, minus 1, 2 minus 1, multiplied by, you can write x1, x2 or xy, whatever it is. 0, 0 gives eigenvector. You can simplify and you know how to find 1, 1. And for lambda equal to 3, we get the other eigenvector 1 minus 1. So here you are able to see that it is a symmetric matrix. It is a symmetric matrix. What do you mean by symmetric matrix? First row is the same as first column. Second row is same as second column. Isn't it? So this is a symmetric matrix. For a real symmetric matrix, if the eigenvalues are distinct, what is important property you have? The corresponding eigenvectors are orthogonal. Can we check that? Here, you find out if something extra that's not asked in the question, but you can have an observation, isn't it? So you just find x1 transpose x1 transpose means column will become row, isn't it? 1, 1. And x2 will be the same. 1 minus 1. So what is the product now? This is equal to 1 into 1, 1 plus 1 into minus 1, minus 1 equal to, isn't it? Implies that x1, x2, Okay, so this way we can verify. Well, a square, a minus 1, a power, that is a inverse and a plus 4a are the same eigenvectors as a, that you can verify. A square has eigenvalues, square of the eigenvalues of a, that's all. 1 square, 3 square, 1 and 9. A inverse will have eigenvalues 1 by 1, 1 by 3. And a plus 4a has eigenvalues 1 plus 4 into 1, that is 1 plus 4, 5. And 5 plus 4, 9. Sorry, not 5, 3. Your eigenvalue is 1, 1 plus 4, 5, and 3 plus 4, 7. These are the eigenvalues of a plus 4. So practice problems. Find the eigenvalues and also the corresponding eigenvectors. So here, the last question of other things you are supposed to do. Last question, for following matrix, find one eigenvalue without calculation and justify your answer. We are now at the towards the end of the session. At least now, can you get any response from any one of you to say answer to this immediately, which is very simple. If you have really followed the session throughout, can you answer? Can anyone? Hello? Hello? Okay, I'll give the answer. Here, if there is a property that if any two rows or columns of a matrix are identical, then its determinant will be 0, isn't it? So here, in fact, all the three are identical. So it is enough, even if there are two that are identical, then its determinant value is 0. So its determinant value is 0 means by another property of eigenvalues, product of eigenvalues equal to 0. So at least one eigenvalue will be, not at least, any one of them will be 0. After 3, because it's a matrix of order 3 by 3, since the product of eigenvalues is 0, so here determinant A will be 0. Product of eigenvalues is 0. So find one eigenvalue which is 0. At least one. But not all. There might be one more, but definitely one eigenvalue will be 0, so that the product is 0. Why product of eigenvalues is nothing but the determinant. Determinant without expansion, I can say it is 0. Therefore, product of eigenvalue is 0. Therefore, one eigenvalue is definitely 0. And justify your answer. That means you verify finding eigenvalues. If you do by taking characteristic equation, solving for lambda, you get 0, 0, 6. Actually, you get two zeros. 0, 0, 6 are the eigenvalues. And trace of A, 0 plus 0 plus 6 equal to 6. And you can find trace of A here, 1 plus 2 plus 3, 6. Okay. This is the justification. And product, if you find product of the eigenvalue 0, which is 0, and of course, which you can verify by finding determinant value to be 0 also. Okay, so you can check. And if there is any query, you can ask, you can get it clarified. Hello? Is there anyone to respond? Yes, come to an end now. Session gets over. Hello. Any queries? Any doubt? Have you all understood? Okay, if there are no queries, then I stop sharing and then end the session. Thank you.
Thank you, sir.
Thank you. Here, GA, somebody has
Thank you, sir.
responded now. Hello. I let you know one thing, Sam, that you look forward to the slides in your teams. Okay. There, the teams I will be posting after every class so that you can view there. I think there you will see the slides will be you get annotated slides. See, that was the.
Okay, sir.
Okay. You check that. You let me
Okay,
know in the
sir.
next class. I hope. So even you have, because I have never got this kind of feedback because they always look forward to the slides that are being posted in the teams. Okay. Immediately after every class. Okay. Now, of course, I have not done it immediately. I will post now together all those. I don't know whether I have done one or two. You just look forward to those slides in the teams. Then you will come to know that they are annotated actually. Is it right? Is it okay?
Okay, sir.
Okay. Okay. Have you all understood then?
Yes, sir.
Okay.
Yes, sir.
Okay, fine. Thank you then. Right.